Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
I'm very happy to have Yoshua Bengio. He's a professor at University of Montreal. He has a Canadian research chair. I've worked with Yoshua for many years ago when he was coming to AT&T for the summer to work on various machine learning problems. And Yoshua has done very interesting contributions. Some of them are negative contributions, which I think are the most useful of all contributions, in the sense that they prove that some things can't be done or that people are not doing the right thing. Today he's going to talk about the curse of dimensionality for local learning. And there he is. Thanks.
Thank you, Patrice. So it's yet another negative thing I'm working on. But in general, I'm a very positive guy. All right. So this is work that I've done with students and collaborators in my lab, Olivier Delalo, Hugo Larochelle, and Nicolas Leroux. And I'll start by saying we're doomed, but I'll end by positive notes on, I think, directions that people in machine learning should pay more attention to if they want to address the really difficult learning problems, if we want to go to things like actual AI. But before I get into the core of the contributions that I want to tell you about, I want to put things in perspective. Some basic notions that we should keep in mind about machine learning and the principles that we use to get generalization, that is to say something about new examples from existing data. So you probably have heard about some of the no-free lunch theorems that have been proven for machine learning. And they say things like that for every learning algorithm there is a distribution P on which it's going to fail to generalize poorly. Or that there is, which is equivalent saying that there is no universal learning algorithm that can be guaranteed to generalize well a priori on anything. So this seems rather negative, and one way that people have reacted to this is to say, well, then what we need to do is to collect a lot of a priori knowledge, to have a lot of domain knowledge about the problem we want to solve, and then apply machine learning in a very constrained way based on that knowledge, and there we may have a chance to succeed. And I think that has gone a bit too far. So there's this underlying belief that one actually needs such strong a priori knowledge to solve any difficult learning task and get good generalization, which I think is incorrect. Of course, at least it hasn't been proven, and I think it's too strong. In particular, I'm going to tell you for most of this talk about an a priori that we use in building in learning algorithms, a principle for generalization that we use in many algorithms. And that is, one way to talk about it is the smoothness prior. So most learning algorithms, most statistical learning algorithms use this. And basically it says in one form or another that if x is close to y, and we're trying to learn a function f, then we expect the function, good functions, to have the property that if x is close to y, then f of x is close to f of y. So very simple thing, we're saying that f is smooth. And this is a very reasonable thing to assume. Of course, it depends greatly on how we define how things are similar, and that's where we get into kernels and other methods that explicitly tell us what it means for x to be similar to y. A direct example of that is Gaussian process methods, in which we are going to say we're looking for functions, and these functions coming from a distribution, the a priori distribution of functions we think are good for our problems have this kind of property. And one way to express this property is to say that the a priori distribution over function has covariance which can be expressed with a kernel that says something like, if x is close to y, then the covariance between f and f of x and f of y is large. So that's one way to look at it. But there are many, many ways to use this smoothness prior. Of course, it's already there in all the classical non-parametric methods like k-nearest neighbors, kernel density estimators, kernel regression, Parsons windows, and so on. So all of these things that are 40, 50 years old, 60 years old, they already use this principle. And of course, all the modern non-parametric methods, supervised learning methods like support vector machines, Gaussian process regression and classification that I just mentioned. There has been a lot of excitement over the last few years on non-parametric methods that are used in different contexts than the usual supervised context, that is unsupervised learning and semi-supervised learning. So in particular, I'll be telling you a bit about manifold learning, which is a subject that I've been spending quite a bit of time in the last few years. And there are methods that you may have heard like LLE, local linear embedding, Isomap, kernel PCA, and so on. Spectral clustering, which is a clustering method. All of these are using this same smoothness prior approach to get generalization. And then there are also a number of semi-supervised learning algorithms that use the same kind of principles that I'll say a few words about. So they all rely on some notion of similarity between pairs of examples. And the notion of similarity may be fixed, or it may actually depend on the data. Very often we need to do some kind of normalization or transformation of our kernel before we can actually use it. And all these kinds of things that people usually call kernel machines, although it's less obvious that the manifold learning methods and the semi-supervised non-parametric methods are kernel machines, but they are. Okay, so for those who don't know already what is manifold learning, very briefly, it's one way to look at the unsupervised learning problem. In unsupervised learning, what we're trying to do is capture some important characteristic of the distribution. And here we're saying, well, we think that maybe the data is concentrated in some regions of space. And those regions we call manifold. So for example, imagine that the data actually lie on this S shape, which is a 2D structure embedded in 3D. So when we get samples, we might get some points like this. And manifold learning is about discovering these kinds of structures. So supposedly low-dimensional structure embedded in a high-dimensional space, which is the observational space. So each point here is an example. And we would like to find where the distribution concentrates. And many of these methods, what they do is they provide, for each training point, a low-dimensional coordinate. So for example, the 2D coordinates of each of those points. They try to recover that from the 3D or, in general, very high-dimensional data. So many of these methods work like this. You take the data, you build some kind of neighborhood matrix where the entries are obtained by applying some kind of kernel to each pair of example. And then they take this matrix and they do some operations on it. They find largest or smallest eigenvalue, eigenvector pairs. And from these eigenvalue, eigenvector pairs, we get an embedding, the embedding I was talking about. But you can also use these. One thing we've shown is that you can use these eigenvectors and eigenvalues to predict for a new example what its embedding should be. And what is interesting is that we see a formula like this, which looks very much like the kind of formula we get for other kernel machines, so that we are in a similar realm of algorithms. So Isomap is one such method. I'm going to skip the details. Let me tell you about semi-supervised learning. So in semi-supervised learning, you have a lot of unlabeled data and a few labeled points. So here is a toy problem in 2 dimensions where each little cross is an example. And some of the examples that have circles, we know they're labeled, and the color is the label here. And so if you only look at the labeled data, you might conclude something like a good linear classifier might be this straight line here. But by looking at the unlabeled data, you would rather choose some decision surface that goes like this, which separates the two half moons. So this is a toy problem that works well on all the non-parametric methods that have been proposed over the last few years, and that all try to exploit the unlabeled data by doing some explicitly or implicitly some kind of label propagation. In other words, we say that if this guy is red, then its neighbors should be also red, and we can propagate that redness, as much as we until we hit something that's bluish, and we can do this formally and minimize some criterion and so on. But in the end, we're using this notion of similarity between examples to propagate the labels, or some continuous variance of the labels. And we can show that, again, the kind of solution we get can be written as a kind of kernel expansion, like I showed before, for unsupervised learning methods. All right. So we have all of these methods, a very large class of methods that are non-parametric. They, when you need to make a prediction, you must look at a whole, either the whole data set or some subset, like the support vectors in the case of SVMs. And they're all based on this notion of similarity that's given by a kernel function. And they're very popular, and they work well in practice in many cases. So what's wrong? So the problem is that they rely too much on only one generalization principle, which is this smoothness prior that I mentioned earlier. And the rest of the talk is going to develop that statement and why it may be a problem. So, but intuitively you can think of it, since we're using this smoothness assumption to help us say something about new examples, well, that's good for test examples that are close to our training points, but it's not very helpful for points that are really far in some sense from our training points. All right. Now, one thing that many people say when I tell them about these results is they say, well, yeah, we have the smoothness prior and we use that, but that's the only thing we can do. That's the best we can do without using very strong prior knowledge. But that's not true. So I'm going to try to give you some counterexamples. So when we say that we like functions that are smooth, we're imposing some notion of simplicity here. But there are other notions of simplicity that make a lot of sense, at least for the kinds of things that humans would like to learn. So for example, think about cosmograph complexity of strings, which is the length of shortest length of a program that generates that string. If we use something like that as a notion of complexity, then that defines a prior based on the length. So things that are small length have a high probability of being good answers. But what we see is that with this kind of prior, functions like sinus or parity are very, very simple, because if you were to enumerate all the short C programs, you would have a high probability of coming up with sinus of x, assuming sinus is in the, let's say it's in C++ or C or something. And parity is just, is a very short program, so it's going to have a high probability. But yet, if you look at it in terms of smoothness, these functions are highly non-smooth. So we see that there are natural ways to describe things as being simple that don't require a lot of prior knowledge, that are in contradiction with the smoothness of prior, that allow us to say that some things are very simple even though they are highly variable. So things like parity and sinus vary a lot, but they have structure. If you learn about if you're able to detect the period of a sinus in some range of space, then you can generalize in a new place, even though you've seen very few examples in that place. If you were to use a kernel-based method to learn about the sinus, you would need to see enough examples everywhere to be able to generalize. And that's a very simple message, but something that many people have not realized. So now let me be a bit more, let's get into this curse of dimensionality idea, which is what's going wrong with using only the smoothness prior. So the geometric intuition is very simple. Suppose we're trying to do something like, for now, just density estimation. So we want to know where is the manifold in the case of manifold learning, or where are the high density places. if we use this a local method that essentially relies only on this smoothness prior, then basically we'll need to tile the space. And in each region where that matters, that is on the manifold, we need to have enough example to know what the density looks like. And if we have to tile this manifold, and this manifold is in dimension d, we may need an exponential number of patches of these regions in order to, in each little locality, to be able to say something about the function we want to learn. Hence the curse. Now this applies not only to density estimation problems, but also things like classification. So for example, if you're trying to do classification, really what you want to do is to characterize what happens on the decision surface. Now, the decision surface in d dimension is going to be a d-1 dimensional object. So it's also, it's also a high dimensional object in general. Now, you may only want to consider the sub-regions of that object where the data concentrates, and then you're back to a kind of manifold learning problem. So in other words, you may be lucky enough that a low-dimensional description of the decision surface is enough. And that's what's going to determine how quickly this is going to explode, the number of data points you'll need to characterize that decision surface. But in general, there might be a growth in the required number of examples in something to the power d, where d is the dimension of this manifold, not necessarily the dimension of the embedding space. By the way, I'm using all these words like embedding and manifold, and I'm not sure if everybody follows me, so I would rather you stop me right now and ask for clarifications, or that I explain some of the terms I've been using. It's jargon that people use in the NIPS community, but I'm not sure that... Okay, so don't hesitate to stop me and ask questions anytime, even if it's trivial things like, what do you mean by this? There are some classical results that I will just briefly mention that show that things like kernel density estimation and k-nearest neighbors classification suffer from this curse of dimensionality. In other words, that you do indeed require a number of examples that could grow exponentially with the dimension. So this is a result for kernel density estimation. It says that generalization error may converge as badly as number of examples to some power of minus something over d. D is a dimension. And so if you invert this, you see how many examples you need to reach a given error level. You get something exponential in d. And then there's something similar but a bit more complicated for k-nearest neighbors. Again, the error goes to something like number of examples to some power minus something over d, d being the dimension. And so you might get a curse of dimensionality. So kernel methods. So now these are classical results, and that says that, well, these classical things may not be doing so well if the intrinsic dimensionality of the data is high. Now, what about new things like SVMs, kernel PCA, LLE, and semi-supervised learning methods, and so on, that have all these forms? In other words, the predictor, the thing that we output in the end, is a function that can be written like this, where we take a linear combination of this kernel applied on a training point xi and a test point x, and some weights alpha I. And the learning algorithm is essentially choosing the alpha i's and the b, and possibly doing something, using the data to do something to the kernel. So the challenge, why it's not so trivial actually to make similar statements for these methods as it has been done for things like classical non-parametric methods. One reason is that the alphas, they may depend in very complicated ways on all the training examples. So for example, in SVMs, the alpha, the coefficient associated to the ith point may depend on the jth point, which could be very far from the ith point. And also the kernel may be data dependent. For example, you may have some hyperparameters that have been tuned, or you may do some kind of normalization which involves all the data. So we've tried to show things like, well, one thing to investigate, to see whether this cursive dimensionality problem applies to these modern kernel methods is whether we really have something local. In other words, if we can show that the value of the function at a point x depend only on the training examples in some small neighborhood, then we're done, basically. Well, almost. I'll tell you more about that later. But it's a requirement. If we have that, and we also have something like in that little region the function is smooth in some sense, then we're done. Unfortunately, it's not so easy to show that. As I said, for example, it's not true that the alphas in support vector machines are only dependent on the neighboring points. They may depend on faraway points. And actually, if we come back to this thing, you see something similar happening, which is that the label we're going to get here may depend on the label here because it's propagating along a bunch of examples. And something like that is also happening with SVMs, that you may have some kind of effect propagating along examples. So that, in fact, you don't get locality in the usual sense. Okay. Now, one simple thing we can say is that when the kernel is local, we can see what happens. One way to think about it is what happens when the test point is kind of far from all the training points. Then the kernel, say, converges to some constant. And if that is the case, we can ask what happens to this predictor f of x. Actually, what happens is that it goes to some constant. But before becoming constant, actually, it may become linear. And that is actually a very interesting property of things like SVM classifiers, which is that if you make the width of the kernel, sigma, which people call sigma, bigger and bigger, the whole thing approaches a linear classifier. Eventually, it becomes a constant classifier.
So you're speaking about Gaussian kernels.
Yeah, but it's essentially going to be true of anything that's kind of local. But yeah, the Gaussian is much easier to analyze mathematically, and most of the work I've been doing is with the Gaussian, which is, of course, a limitation. So we can easily do things like compute these limits and look at what they look like, look at them for the Gaussian. So why this consideration is interesting because in a very high-dimensional space, we might expect that our test point is kind of far from most of the training examples. So that this situation is not so far-fetched. But OK, so it's only giving us some intuition that something may be going wrong when we are far from all the training points, because the contribution of if all the k's get a similar contribution, then we're in trouble.
Joshua?
Yes?
They might be all equally far, but not in terms of the sigma of the Gaussian kernel.
Well, you mean if they have different sigmas, or?
No. In other words, you're saying they're all equally far away from a test point. That's true.
Right. Not in terms of the sigma, right?
Yes.
Yes. So if sigma is large, but then they all kind of have a similar influence. That's essentially what's going to happen. Mm-hmm. And then that's how you get into the linear classifier regime. Now, OK, now I'm going to tell you about the first result that we have, which actually is mathematically very simple and derived from an earlier, a bit more powerful result that people have shown before, that gives a very strong hint about the cursive dimensionality for these local kernel machines. And it's been, the proof is only for the Gaussian kernel, but hopefully we can generalize mentally to other kinds of local kernels. So before I give you the result, the idea is that consider, say, classification problems where the decision surface is, say, this red line, this red curve, sorry. And we're going to characterize how much it varies by drawing a straight line that crosses the decision surface a certain number of times. And we're going to count how many times we can cross the decision surface. So you can see that if the decision surface is very smooth, now we can't find a line that crosses it many times. And if we can find a line that crosses it many times, then we do have something that varies a lot. And we're going to make a statement about how many training examples you need to classify with some error level if the decision surface varies a lot, so that it crosses this line many times. So the statement is like this. If we can find a line in RD, so that's where the data lives, that intersects m times with the decision surface S, then one needs at least m/2 Gaussians to learn S with a Gaussian kernel classifier. So in other words, to represent that decision surface to some precision, you need to have a number of non-zero alphas, that is a number of support vectors in the case of support vector machines, or in general a number of training examples that grows linearly with the number of times that we can cross this line. So if we have a line that wiggles a lot, we'll need that many examples if we use a local classifier of the Gaussian type.
Does it generalize to higher dimension?
Yeah, it's for any dimension D,
Oh, I see.
right? I mean, of course, here this is a drawing, but so for any dimension D, if the function we're trying to learn, that is the decision surface, wiggles a lot and we can find a direction that crosses many times, then we need many training examples. How many? Well, that's how many times we can cross, basically.
There are two lines, for example, one in one direction that crosses m times, another that crosses m. That's how it goes with this time.
No, I can't say. So it's going to be the minimum of the two, right? I mean, it's going to be at least whichever one line, detects. I would like to have a result that says what you are saying, and we're working on that, but not so obvious. So it would be, basically, we would like to generalize from a straight line to a curved line. You would think that if you find a smooth curved line, that intersects many times, then that would work also, but it's not so easy to prove. But I believe it's true that if you have some smooth curved line, it's going to work. But you can see that if you have a non-smooth line, then you can do whatever you want. It becomes meaningless. So it's not so trivial.
But in that case, I mean, the problem is that your kernel is local. It's Gaussian.
Yes, that's exactly what I'm trying to say. Yeah.
So are there better kernel to use if you know that?
We'll see by the end of the talk if that is possible. Yeah, basically my message is going to be we should learn some kernels that are going to be non-local, so that what you learn in one place can tell you about the other place. The idea is that essentially the problem is we can't say anything about a region where we don't have any data, even though there is some generic structure here, and that if we learn something generic about the shape of this decision surface here, we could potentially generalize here. If we don't do that, then we're stuck and we'll have to to cover the space, basically. I mean, one thing is it's easy to make the kind of statement I just made, which is kind of vague and intuitive. And the other thing is to prove theorems that have a precise, So, but I think this one is giving pretty strong evidence that something's wrong. We have another theorem that is specific. I didn't do that. My grad students did that. And they did all the visuals. So we can prove something about parity. Now, parity is interesting because it doesn't fall into the previous category. In other words, there is no one line that we get many variations, because essentially you just have two values. The parity is the binary function that assigns 1 or minus 1 depending on the number of ones and zeros in the input. So you can think of having a big hypercube, and we're just caring about the corners in which quadrant you are to decide the output. What's interesting about the parity is that if you have one input vector all of its one nearest neighbors are of the opposite sign. So in other words, the answer for one example is exactly the opposite for any one of its one nearest neighbors. So it varies a lot in that sense. So basically the theorem says that you need an exponential number of examples, so an exponential number of Gaussians or spot vectors or whatever in your expansion to learn the parity function.
So why can't you just stick a very thin Gaussian over every point with a plus or minus 1 and sum them up?
Well, so if you stick a Gaussian over every point, then you need an exponential number of, I mean, there's an exponential number of inputs.
See the number of...
I mean, if you're in D dimension and you're trying to learn D parity, there's 2 to the D possible input vectors. What you're saying is put a Gaussian over each one, and well, okay, actually you don't need to put over each one, just one every 2, but that's, yeah. Actually, you just need to put one on the plus ones, and then the bias is going to do the other, right? So, yeah.
So how many Gaussians you need for a step function?
For a step function?
Uh-huh.
Well, step function doesn't vary a lot, so you don't need many Gaussians.
So how many then?
Two. One, I guess.
Yeah, just one Gaussian. The thing is, we're taking the sign, so...
No, you need two, because otherwise it'll be round.
Yeah.
Oh, yeah, maybe. Anyways, I think when it really becomes interesting is if you're trying to learn a complicated function, something that looks complicated in the sense that it varies a lot. And the thing about dimension is just an artifact. I think this curse of dimensionality should be really called the curse of variability. So if you're trying to learn something that varies a lot, then you're in trouble, whether it's in one dimension or in 100 dimension. The only thing in practice is that things in one dimension usually are simple, and things in 100 dimension are more complicated. I mean, that's sort of the folk assumption, which may be wrong. And in 100 dimensions, it's easy to get something complicated by taking a bunch of one-dimensional thing and combining all of them, that, like parity, for example. So you can get an exponential number of variations by combining just binary variations in one dimension. That's what you get with parity. All right. Let's move on. Okay. So I've said that, but now what I would like to do is to kind of generalize, or make a statement more generally that one should note that there are many functions with low Kolmogorov complexity, like the sinus and parity that I talked about. So these are functions that are simple in some sense that humans comprehend. They're simple for humans. And yet they would require many training examples for a Gaussian kernel classifier to achieve some error level epsilon. And we can make the required number of examples arbitrarily large without increasing the Kolmogorov complexity. So this is just a consequence of the previous theorems, that there are functions that are very simple in some sense, which is Kolmogorov complexity, and yet require as many examples as you wish, depending on how you set up the problem. Okay, now let me tell you quickly about semi-supervised methods. So there are a bunch of these methods. I mentioned the idea of these, and many of these turned out that we can express them in a simple framework in which one minimizes a quadratic cost, which trades off between smoothness. So we're trying to say the value of the function at two neighboring points should be close. So f of xi should be close to f of xj if xi and xj are close. And fitting. So we would like f of xi to be close to yi if there is a label yi. So if we take these two things together, there are many variants of these methods that fall into this quadratic, very simple framework. And for this, we can prove a theorem that says that after running the label propagation, that is solving and finding the predictor, the number of regions with constant estimated label is less or equal than the number of labeled examples. So it says that the number of examples, of labeled examples that we will need, is at least equal to the number of regions with constantly estimated label. What that means is regions where, so if you imagine, say, a one-dimensional space here, and here we have the predictor says plus, here minus, here plus, here minus, then these are regions with constant sign. And how many regions we have? We need at least one labeled example per region. So it's a very simple statement. But what that means is that if the function we're trying to represent has many of these variations, many of these regions, then we need that many examples. So again, it's a same kind of result as the one I had before, except there's no notion of a line here. We just need to be able to define these regions of different sign. The last thing I want to mention, I guess we started at 22 or something like that. Okay, I would like to mention. Yeah. So yeah, I'm fine. The last thing I want to talk about before I get into sort of kind of how do we get out of this problem is trying to define a notion of locality for things like SVMs, where actually the function may be not local, but we might still be able to define some notion of locality. And so this is something we're working on, and it's based on looking at the derivative of the function rather than the function itself. So we have this kernel function. Its derivative looks like this, derivative with respect to x, the test point. So now this is a vector, and we have here vectors as well. The alphas are scalar, I remind you. And we're defining a notion of local derivative kernel. We're saying that a predictor is local derivative if df dx is approximately contained in the span of the vectors x minus xj, where xj is a neighbor of x. So what this says is that if here we have a test point x and it has some neighbors x1, x2, x3, we're saying that df dx is a linear combination of these difference vectors x minus xi, where the xi's are these neighbors of x. So if we can write something like this, then we say we have this local derivative property. And you can see that if that was the case, then we have some notion of locality. Even if the function is not local, what we're saying is that the vector, this gradient vector of f, if we have this property, then it's defined, essentially, it's constrained to be in some subspace defined by its neighbors, the neighbors of x in the training set. So if we have this property, then we do have some kind of locality, which applies even if the alphas depend in complicated ways on all the training examples. And
restrictions on the gammas, or the gammas can be negative, positive, large?
Okay, so the only restriction is that we're going to the gammas are essentially alphas times some derivative of the kernel, some variant of the kernel. And so for this to work, actually, usually we'll need the alphas to be bounded. So if the alphas could be arbitrarily large, then this is not going to work. But mostly we only need the alphas to be bounded, which you usually need for good generalization, for example, for SVMs. So what is this df dx? What is the geometric interpretation of this derivative? In manifold learning, f of x represent the embedding. So we're going to have multiple functions f, say f1, f2, f3, where f1 is the first coordinate on the manifold, f2 is the second coordinate, and so on. So df dx is actually, df1 dx is a tangent vector for coordinate 1, df2 dx is a tangent vector for coordinate 2, and so on. And so all the df dx together span the tangent plane of the manifold. And for classification, what is df dx? So f now is the discriminant function. So it's the function that we're going to take the sign of to decide which class we are. And so here's decision surface. We have a point x on the surface. df dx is the normal to the surface at that point. It's the direction where you can move x to have the largest increase in the discriminant function or the largest decrease. Okay, so that's the geometry of df dx. And that gives us a hint that if we have this property, then it's if x lives in a high dimensional space, I'm not talking about the manifold dimension, but the embedding dimension, the ambient space. So if the data is really high dimensional data, then if we have a few neighbors, it's easier to see in the previous picture. If we only have a few neighbors, and X is in the high dimensional space, so the ambient space here, 3 is not very high here, then that would be a very strong constraint. In other words, saying that df dx has to live in this subspace, say 3-dimensional subspace. If we're in 3-dimensional space, then it's no constraint at all. But if we're in a 1,000-dimensional space, saying that df dx must be lying somewhere in this 3-dimensional subspace is a very strong constraint. So in that case, we would have a strong locality argument. Okay, and we can show that SVMs with Gaussian kernels are local derivative, have this property. LLE is local derivative, Isomap is local derivative, kernel PCA is local derivative, spectral clustering with Gaussian kernel is local derivative. Right, so as I said earlier, one step to say something about the cursive dimensionality is to have some locality property, and we've just explored one. The other thing we would need is say something about smoothness. So in all of these algorithms, we can choose how far we take our neighbors. For example, in SVMs, we can choose the width of the Gaussian. So one could say, well, we could just choose sigma very large. What's wrong with that? Then we don't have locality. Well, the answer would be that if you choose sigma too large, then you can't fit functions as well. So you need to show that. And that's kind of empirically obvious, but one would like to make mathematical statements about that. And if you can do that, then essentially you can argue about the cursive dimensionality. Okay, I'm going to skip all this. So we have a result that says something about the smoothness of Gaussian kernel classifiers as sigma becomes large. Essentially, for SVM, so when the sum of the alphas is 0, then the decision surface becomes linear. And if we don't have this constraint, then we have a quadratic surface, but it is very constrained. It's the quadratic surface which comes about from the normal vector being a linear combination of two simple vectors that are the sphere normal vectors of spheres centered on the examples of each class. Anyway, it's basically saying that there's a very strong constraint on the kind of decision surface you can get if sigma becomes large, which makes a lot of intuitive sense.
Okay, so you've shown that if sigma is too small, it's terrible, so you get the cursive dimensionality. If sigma is really large...
No. I see where you're getting.
Papa bear, mama bear, just right, you know what I mean?
No. Yeah. Because, see, if... I don't need sigma to be very small to go to... If... okay, so let's say that sigma is too large. And that sigma, say, is about the diameter of the data.
Well, I don't know. I don't have the exact representation of that. But you're saying it as it becomes large with respect to the diameter of the data.
Yes,
That's not large with respect to the diameter of the data. That is the diameter of the data.
But even for equal to the diameter of the data, we get something that's... I mean, of course, you can't make limits, right, if you have sigma equal to the diameter of the data. But you can see what happens. What are the dominant terms in the expansion?
I understand, but there could be reasonable behavior in between the two limits.
Right.
In fact, I think that's where most people run.
Yeah, that's exactly where most people run SVMs, with sigma on the same order of the diameter, some fraction, large fraction of the diameter of the data. Absolutely. And that makes a lot of sense, because that's where you're least stuck by these problems. Right.
So, I mean, you haven't proven
No.
that SVMs don't work. It's just that,
No.
okay, don't make sigma too large and don't make sigma
But
too
the point I
small.
was trying to make here is that you don't make, for any sigma that, well, not sigma, let's not talk about sigma, but let's talk about, the size of the ball that contains neighbors that have a strong influence on this df dx, for example, okay, which is dependent on sigma. But as long as that ball doesn't include all the data points, but just say some fraction r, then you do get a cursive dimensionality. In other words, if you're trying to tile a big sphere with a bunch, so let's say I have a big sphere here that contains all the data, and I'm going to try to tile it with spheres that are just a bit smaller, I will need an exponential number of these just slightly smaller spheres to tile the whole space.
But you don't, again, only need them if your function were complex. In other words, the whole argument is relying on the fact that you have to tile because you have to...
All right, of course, yeah, it depends what you're trying to learn. If you're trying to learn something simple, then it doesn't matter. If you're trying, for this thing to work, you need to say, I need to be able to choose the value here kind of independently from the value I've chosen, just a bit off here. If that's the case, which means that my target function varies a lot, then I need to tile. Otherwise, I don't need to tile, right? And the reason why SVMs work in practice is that you don't need to tile for most of these problems.
Yep.
Okay. So the good news from this analysis is that, well, okay, so SVMs are actually doing something smarter than k-nearest neighbors, because when sigma is large, you get close to this linear regime, which is actually a global classifier that allows things to interact from a large distance. The only problem is you're stuck with smooth functions. But it's something in between which is you're able to trade off pretty well. Yeah.
So the problem is if the function is too variable, then you cannot learn it well with Gaussian kernels.
Yes.
I mean, then it has nothing to do with dimensionality, because
you're right.
Even for dimension,
it's just easier to make arguments about dimensionality, and people have been used to that. But fundamentally, it's the variability that matters. You're absolutely right.
Yeah. Then the question is, how often do those functions really appear in real life? Let's say for computer vision, like you can have a function where you assign value 1 to all rational numbers, and value 0 to all.
Okay, you're too extreme. You're too extreme. Let's just think about it differently. If you're trying to generalize to instances that are not very close to the training points, but that share something about the structure, there's some shared structure behind these things, then using a local method, you're going to fail. So it doesn't have to. You don't have to go to rationals or something, some crazy functions. It could be something as simple as vision, right? So if you think about vision, there are many, many factors of variations that are compounded, that give rise to the impossibility of sampling enough data to cover all these possible variations. So if you think about, say, complex objects that have parts, and all of those parts can be in different kinds of configurations. And then you have things like, of course, illumination, the geometry, the size, and where the camera is, and all the things that can happen in the background, and combinations of multiple objects, and so on. Then this is a combinatorial explosion. If you try to do this locally, you need to have to sample the space, in a way that doesn't make sense, even though there are some simple things behind all of this that kind of generate the data. And we would like algorithms that can discover these things. Right. So is there hope? Well, humans are able to learn such things. And I've talked about examples of functions that are simple, but we couldn't learn with local learning methods. So are there non-local learning methods? And yes, there are, but there's probably not enough work on them. So briefly, I'll take 5 minutes to tell you about some things that I've been doing recently and some things that are ongoing to try to do kind of non-local parson windows or non-local kernel things. And the idea is that we're gonna learn something about the geometry of the space, like we do in things like parson windows or manifold learning, but we're going to learn it in such a way that what we've learned in one place could be applied possibly in other places. And the way we've and many ways, of course, to go in this direction, but the way we've looked at is we learn a function f of x that for a point x tells us about what is the geometry of space in the vicinity of x. So more specifically here, we're saying at a point x, what are the directions in space where I expect to find neighbors of x? So one way to think about it is, if I were to place a Gaussian around x, what would be the shape of that Gaussian to have the neighbors as close as possible to that Gaussian? In other words, what is the Gaussian that would generate the neighbors of x? And so f of x describes that Gaussian. In the version that that is in our last NIPS paper, we just find the principal directions of the covariance matrix of that Gaussian. In a more recent work, we actually generate the whole Gaussian. So we generate not only the principal directions, but the variance and the mean and so on.
MLP is not local, MLP. I mean, everything can...
Well, we can't say much about MLPs.
It's always non-local.
Right. It might be non-local, but it might be local. I mean, we can't prove that it's local. That's all. But
every sample in the training
has an
affect
influence. Yeah, but
the weight, right? I mean, just by
it might be non-local. That's all we can say. Whereas we can say for sure that, say, a Gaussian kernel predictor is local. Yeah.
But there is theory that says that the MLP doesn't have the Gaussian image now.
Yeah.
Yeah. So maybe everyone just use thermal errors.
Maybe. So that's what we use here. And so I'm not going to tell you the detail of how we train this and so on, but just to give you a flavor of what happens, we trained it to predict the neighbors of points that were digit images that were slightly rotated. And so the network predicts where it should find neighbors, which means what kind of transformations you get by doing a slight rotation. And then we can see what kind of transformations it learns. And the interesting thing is we can train it on digit images and then test it on letters, which are very different in terms of the Euclidean distance. And it is able to find essentially rotations of these letters, to predict rotation of these letters. Whereas if you use a local methods based on the kernel predictor, basically you can't do anything because this letter is just too far from all of the training points that it has seen to do something meaningful.
So all this is premised on choice of Gaussian kernel for SVMs, right? And there are all sorts of other kernels.
Sure. Well, you'll see. I mean, what we're doing here is learning a kernel, really. Right. One way to think about it is we're learning a kernel. So in fact, so more formally, what we're doing here is we're learning a density that is like a partisan density, except the normals have complicated structure where the covariance matrix and the mean are functions of the test of the training point. They could also be a function of the test point, but that's another story. And so essentially, this covariance matrix is a kind of kernel. But we're learning it. That's the difference. And the parameters of the function that gives you the kernel are non-local. So they generalize to places you've never seen. Let me give you an example of what happens with this. I'm going to skip results and just show you some. So here's a sinusoid. If you do try to learn the density with, say, all kinds of Gaussian mixtures, well, what's going to happen is you're going to have some holes, and with this method, somehow it seems to find some global structure that generalizes. This one is not so hard to learn, but still it does much better than all the local methods we've tried. This one is another thing that's easy to visualize. So it's predicting where the density is, and this is what we get with our non-local manifold partisan predictor. This is what you get with Gaussian mixture. This is partisan windows, which makes these blobs around the training points. And manifold partisan is a variant of manifold partisan in which we also learn the covariance structure, but based on the data around each point. And it does a pretty good job, but it doesn't find such smooth functions as this one finds. Yep.
There's two issues. One is if you have the prior knowledge that there's a sign underneath it between them.
But we don't use any of that prior knowledge. Of course, if you had that, it would be very easy.
The thing is, for example, images you just showed, there are image kernels based on pyramids that look at the whole image. Right?
Yes.
So if you know the problem needs that kind of correlation,
yeah.
just use kernel.
Yeah, sure. If you do, but the problem is if you don't, what do you do?
Sorry?
What if you don't know that it needs that kind of correlation? Okay, but that's kind of, it's knowledge engineering. It's domain dependent, and I want to discover generalization principles that allow to do non-local generalization, and yet are very broad. Okay.
It's very interesting to compare that with the domain version, right? For images.
Well, I mean, anytime you have domain knowledge that is specific to a domain, it's going to be better than some, very broad a priori. But the problem is, what do you do when you don't have that much domain knowledge? Or the domain knowledge, even in one application, is going to be very specific to one aspect of the application, but not necessarily everything about it. So you still want to have some generic principles that you could apply in this case.
So what you're saying is that, the awesome distribution from which this algorithm will be based. We know that that's the first thing.
Yeah.
There's the smoothness principle that lead to the locality,
Yeah.
and that's bad for other reasons. And you have something in between, which is the Kolmogorov complexity,
Right.
in which you have
Broad prior is very broad. So it's not very specific, the Kolmogorov complexity. It's very broad.
But the simplicity of the algorithm is already induced some kind of another topology, right? There was the smoothness, which is a smoothness
Yes.
in input space. Now you're talking about the smoothness in terms of coding.
Yes.
And you're trying to build a
Right.
principle to learn those, to learn problems.
Well, I'm saying that we should look for alternative definition of simplicity beyond smoothness, and that we need these if we want to be able to generalize non-locally.
Without breaking the first thing, which is that we won't have a...
Well, for sure we won't get a universal machine, but we might get a machine that works well on this planet with the laws of physics that we have here. And that's probably enough for us.
So that means there is free lunch on this planet.
Oh, for sure. I mean, we are living proof of it, right?
I mean, I guess it seems a little bit like, so no, like Patrice said, so you no longer may have smoothness in the functions in the input space itself.
Yes.
You still have sort of smoothness in the type of variability. Is kind of what you're hoping for, right?
Yes.
The thing in question
We need some kind of higher order notion of smoothness, and it may be very domain dependent, and that's fine if you have it. It's great, but it would be nice to have some more generic. I mean, I'm not saying that there's going to be one principle that's going to solve everything. We should discover a number of these that have as broad an applicability as possible. So one example that I've been thinking about has to do, inspired from humans, is that we learn complex functions, but they're not arbitrary complex functions. They are complex functions built by combining simple functions. Right? When you write a mathematical expression, it's a combination. It's a composition of simple things, and not every complex function can be written like that. So what I'm saying is that there may be principles like this which we could exploit in particular learning algorithms that restrict the class of functions we are willing to explore. In other words, that define a notion of simplicity that is very different from the notion of simplicity we are used to. So the thing is, smoothness is fine, but it's just too restrictive. We have to do, open our horizon to other kinds of notions of simplicity to discover other principles for generalization.
But the thing that bugs me in what you're saying is that you seem to say that there is an objective. There's an objective simplicity, and I think
No. I'm not saying that. I'm saying that there are some notions of simplicity that are different that may allow to work well for some large class of problems.
How can you say that they are prior independent?
I'm not saying they're prior independent. I'm saying the game here is to discover generalization principles that work well for the kinds of problems we care about. That is, if I want to do AI, okay, so I care about the kinds of problems that humans solve well. And that's a restricted class of problems. It's large, but it's restricted. So what are we doing? I mean, we're looking for learning algorithms that work well on the kinds of tasks that we care about. That's all. And we would like to find principles behind these that work over a large variety of tasks.
Well, you talk about you work on the problem that you care about. Why don't you spend more effort looking at the domain knowledge? I think that probably would give you more gain than looking for general.
But I'm not saying that you shouldn't do that. I'm saying that it would be even better if we can also discover principles that have a much wider applicability. So the thing with very specific domain knowledge is that it doesn't translate very well to other applications. But the kind of priors I have in mind would have much broader applicability. So I'm not saying you shouldn't do domain engineering. You do need to do it if you want to have the best possible system for a particular application. But it would also be great to have something more general.
I love the wide applicability, but the domain doesn't have to be that domain dependent. I mean, if I'm dealing with an image, I can just take products of pixels and that would be my kernel, and that will generally help if I do it in a reasonable way for any image, not particular.
So it's already a large domain in some sense. Yeah.
And you could argue that you're pointing at humans, like look how good humans are, but humans are very good at making decisions based on specific sensory modalities, which have their specific domain priors. So you can't say, oh, look, the humans are general.
But they generalize across sensory modalities, though. So, for example, I've been looking a little bit at the infant learning literature, and you can learn grammars and generalize across sensory modalities. So if you learned about the structure of some texts using one sensory modality, you can detect that things satisfied as grammar even if they come from, in a very different form. I mean, just like we have visual input of language and auditory input of language, and we generalize across these two modalities.
So you're arguing to define the complexity of a problem by smaller building blocks you already have.
Smaller what?
So you said we don't want to define the complexity of a function just by distribution. We define the complexity by some building blocks, such as psi x.
Okay, well, that's an example, yes. That's one way to go about it.
But how do you define the complexity of those base class kind of building blocks?
Well, go ahead and try it. I mean, that's what research is about, to find learning algorithms that work, and we'll need to define specifically, precisely what we mean by complexity or...
Well, I mean, there's lots of examples. Like, let's take a convolutional neural network.
Yeah.
So you have a convolutional kernel that's trainable, and what it learns in one part of the image will be applied in another part of the image, even though there may never be an example there. So this is
a highly non-local generalization. Absolutely.
So are you advocating that we formalize that kind of...
Well, I'm advocating that people waste less time. If their goal is to learn complicated things like we need to do in AI, then we should waste less time on local methods. And now, depends what your goals are, right? I mean, if your goal is to get the next NIPS paper, then maybe it's not the right criterion.
The reality of the convolutional neural network if you're doing it because you believe in certain kinds of generalization properties for images, that you believe that there's a convolutional kernel that might be consistent across different, or just like your rotation.
I mean, everything is domain dependent. The question is, what is the size of that domain, right?
The next thing is that there's no convolutional equivalent for support vector machines. So maybe the next thing to do is, why don't we work on that, right? And that's probably what you're saying.
Actually, I am working on convolutional neural nets that can be applied to non-image things. But anyway, that's another story.
Perhaps I've gotten lost in the details here. Could you take a step back just for a second and summarize the principles that you've identified here that are more general than that?
You're talking about the part of my talk describing the problem with local methods?
No, just...
Or the end of the talk here with the...
Maybe I'm just waiting for the punchline and the conclusion slide.
Okay. Conclusion slide.
No, you don't have to fast forward there. If you could highlight the high-level lessons.
Okay, so the lessons are that there is a very large class of learning algorithms that covers supervised learning, unsupervised learning, semi-supervised learning, that all seem to rely on this one simple principle, which is very broad, the smoothness principle. And it's not very surprising to many people, the kind of results we've obtained, but to others it comes as, that actually these methods have limitations. And the limitations are essentially that it's hard for these methods to generalize far from your training points. And in particular, if you're trying to learn something that varies a lot, in some sense, even though it may have a very simple structure, it's going to be hard to learn in the sense that you will need a very large number of examples to generalize. And however, it doesn't mean that we have to use these kinds of methods. There are other ways to learn that are non-local and have the potential to generalize better to these complex tasks. And I've presented some examples, but I think there's a wide open field of many different possibilities there. So nobody's angry at me?
One more question. Talking about smoothness, in the beginning, you actually didn't even define smoothness because approximation.
Right, of course. It depends on the notion of. To define smoothness, you define smoothness formally when you define this kernel, for example. That's where you get smoothness.
The kernel has a sigma, or if sigma is large, then it's not as smooth.
Of course,
as the other one. So you don't think that principle can be generalized? I mean, some problem may not be, may not have that, strictly smoothness. It may not be that local, but if you make the, sigma large enough, it actually cover more space. So can that be generalized?
Not sure I understand the question.
Smoothness problem in general is good. A lot of practical problems.
I'm not saying it's not good. I'm saying that it's not sufficient to get generalization far from your training points. That's what I'm saying.
But if you relax the parameter that defines how smooth it is, like single in the Gaussian kernel, how far can it go?
Well, the thing is, you're going to have this trade-off. Either you choose sigma very small, and then you are able to represent highly variable function, but then you'll need an exponential amount of data, or a large amount of data, depending on the complexity of the function you want to learn. Or you choose sigma large. If you choose sigma large, you need less data, but you can only learn very smooth functions. That's what this. Very simple.
All right, so let's thank the speaker for a nice negative result.